All right, so for number 2, the key here was this. First of all, focus, guys, focus. You needed to know the mass of the planet itself. Okay, that's one thing I gave you in class yesterday, and the radius of Pluto. Okay, if you remember, I wrote it up on the board at the end of class yesterday. You needed those facts. They weren't in your textbook. That's why I gave it to you. Which is, yeah, I didn't think Pluto was even included there. I didn't even know it was. So G is a given. This is the exact same thing as the first problem. Literally, this says, how far is the moon from Pluto? So we're looking for that altitude or the height. So we find the actual distance r, which is the distance from center to center, and then we drop off the radius to get the height that's missing. That's this part here. Same thing here. It's the exact same problem, except the numbers just change. G is the same. It's the same no matter what. The mass changes. The period length changes. Now notice, it was 153 hours. So whenever you're given in hours, you multiply by 60. You multiply by 60 first to get it to minutes. So we multiply by 60, that puts it in minutes. But we want it in seconds, so we multiply by another 60. So really we have to take this number to go from hours to seconds and multiply by 3,600. And this is what you get in seconds. So that's the time period in seconds. That's going to go in for a T right there. This is the value of G. That's going to go in right over here. The mass of Pluto. The mass of Pluto loops in over here. That's some crazy colors, sorry. Now the radius of Pluto, notice, the radius is not used. Again, it's not used until that last step. That's your different problem, guys. Same formula. For the radius of the planet, you're not actually going to utilize it until you get the actual distance between the planet center and the satellite. Once you get the distance between them, okay, the distance, which is this number here, 8.7, I'll write it over here because I know you can barely see the highlighting. 8.7 times 10 to the 7 meters, that's the distance from the center of Pluto to the center of Pluto's moon. Okay? Now, we want to know how far apart they are. The issue with this problem is that we don't have the radius of the moon. So we can't drop off that radius, or else we really should. Again, remember, this distance from here to here is the value of r. What we're looking for is the distance from here to here. So really, we should take the whole r value, which is what we have, subtract off the radius of Pluto, which is this blue part right here, the radius of Pluto. And what else should we really subtract off? The radius of the moon. But we don't know the radius of the moon, and it's such a small moon that it's insignificant. You don't actually use it. Just like a satellite. If you had a satellite up in space, technically, to get to the satellite, you have to take off the radius of the satellite, whatever the radius would be. But it's probably like 20 meters for the satellite, so we ignore it. Here, we're not given the radius of the moon. So for here, you would normally say, yes, also subtract off the radius of the moon, okay, to get the actual distance in the middle. But for this problem, we didn't have it, so we simply took the radius minus the radius of Pluto. Okay, again, the radius r is actually the distance between them. We call it radius or r, but it's really the distance between the centers. Let's go on to the third one.
Does it matter like how many, if we do like 8.5?
If we do 8.5.
Instead of like 5.
Sure, it's fine. Because at this point, you're times 10 to the 7, so those other decimals are not significant at all. Okay, because it's on the order of magnitude of millions here. Okay, so it's around 80 million meters, whatever that would be. It doesn't matter what it's 85.4.
Like I tried to solve it analytically.
Okay.
And I got confused on the part. Like I got 2, like t over 2 pi squared times gm, and then it was equals r cubed.
You could do the cube root like this. That's what this is here, or raise it to the 1/3 power. So Bridget, if you'd like to, instead of using the cube root, you can write it this way with this whole thing to the 1/3 power, and then you don't have to worry about the cube root at all. Okay, if that helps you. And in the calculator, remember, when you raise it to a fractional power, what do you have to put around it? Parentheses. If you don't, it's going to raise it to the first, and then it's going to divide by 3. Is you do that? Okay. Again, parentheses. Because it raises it to the first, and then it divides that answer by 3. So you're getting 1/3 of whatever that number is instead of the cube root of it. Okay? Third one. The orbital radius of a satellite in geostationary. Geo means what?
Earth.
Earth. So if you didn't know that, you could have removed it, but I told you yesterday. So this is geostationary. The radius of the orbital radius is 4.22 times 10 to the 7. What is the orbital speed of a satellite in geostationary orbit? Let's take a look at this problem. This is very, very interesting to look at. Here's the reason why. If it's geostationary, what should the period be? What should the period be of this?
Negative. 24.
It's geostationary. What is the period? It is moving.
Oh, it's Earth's.
What is Earth's period? What is it?
24 hours.
24 hours, or as Houston said, a day.
24.
Okay? You didn't give units. 24 hours or a day. You said 24 or 2 or what?
I said 24, 365.
Ah, okay. It's 24 hours. So again, we're not solving for t here. We're not solving, but just keep that in mind, okay? Again, if a satellite moves with the Earth, how long does it take to get around the Earth? 24 hours, because the Earth is moving with it. Okay? So, geostationary. Now, we start by knowing the value of g. If it's geostationary, the central object is Earth, so we use the mass of Earth. We're given the geostationary orbit, it's given right here, 4.22 times 10 to the 7. Okay? But again, Karen, this says the orbital radius. So what they're giving you already is the mean radius of the Earth plus the altitude. This is the Earth. This is the radius of the Earth. This is the additional distance. This is the satellite. Now, this problem gives you the entire value of r. Okay, again, take a look. This is the value of r. That's what they're giving you here. It says orbital radius. Orbital radius is the radius of the central object plus the altitude. That's what the orbital radius is. This r, remember, we define that as orbital radius. So the orbital radius is the sum of these two. So you're already getting that value. So for this problem, you don't have to subtract off or add on or do anything with the Earth's radius. Okay? Again, you're given the value of r. Orbital radius, that's what r means. So we simply plug in that value there. We plug in the mass of the Earth. We plug in g. We take the square root of the product of the quotient. Right? There's a product on the top and a quotient. We take the square root of that and get a number. Now, so we don't need the Earth's radius here. We do not need the Earth's radius. This happens to be the velocity of somebody. So you want to know how fast you guys are going? It's probably a little bit less than that. That's how fast we're moving right now. Maybe say 3,000, I would say, if I'm estimating, meters every second. Every second you're moving 3,000 meters because you're moving tangentially. You're moving, the Earth is actually rotating. You're not physically moving. You have no displacement, okay? But relative to the surrounding atmosphere, we are moving. We're moving at a rate of around 3,000 meters per second. Now that's the satellite, obviously, so that's why we're less, because we're further in. Further out, you're moving faster.
So if Earth stopped rotating suddenly, would that be shoot out?
Sure. If Earth stopped rotating, we would need such a change in acceleration, a negative acceleration to stop velocity, which induces a force. Remember, F equals ma? So if there's a negative acceleration to stop the Earth, we would feel this like throw forward, and we would all be shot forward. If it just stopped.
Where do we go?
Depends on how. With this kind of a velocity, tangentially to the Earth, there's a chance you might careen off the Earth into space. Because this is the if you went from this, and like a super like giant came in and just stopped the Earth instantly, like it was a basketball, like it just caught the Earth, you might just shoot off the Earth. Because this would be like your initial velocity, right? And you'd be shooting off at that velocity, tangential. Is that what that is? It's only 60 miles an hour?
Well, I mean, like,
converted that.
Yeah,
sure.
That's like less than
3,000 meters every second.
Yeah, so that's like 2 miles per second.
What's a mile, guys? How many meters? 1,500?
Yeah.
So it's a little more than.
Miles only 1,200 meters? I thought a mile was 1,500 meters. Approximately. Pretty sure.
1,600, yes.
Okay, yeah. So that is about, but that's about 2 miles a second.
Right.
2 miles every second.
Times that by 60, right?
You got to go from seconds to minutes to hours. Times 60 times 60.
Every
So
second
this is
we
2
go
miles a
by.
second. Times 60 is 120 miles per minute. Times 60 after that. That's 7,200 miles per hour. So we're talking, an airplane flies at 500 miles per hour. 500. Okay? So at this speed, which ours would be less, of course it would be, but still, we'd be looking at around 7,000 miles per hour. That's the speed you would shoot off the Earth at. Which would probably be enough to get you into the atmosphere, you would burn up in the atmosphere, your body would vaporize, and you would never make that. Sorry.
Only if you're really
Here.
Only if you're really
If this feels better, guys, how about this one?
Unless you were 1,000 pounds, you would just lose weight.
Hypothetically, right? How about this one? You make it out to outer space, but there's no air out there, so you suffocate. So you want to vaporize or suffocate?
I want to vaporize.
I'd rather completely vaporize into nothing.
Would it hurt?
You ever seen The Rock?
Yeah.
The movie The Rock? At the very end, he's like, what happened to Sean Connery? What happened to his name? He's like, you got vaporized? People can get vaporized. You can, if it's a high enough temperature, your body just melts off. Becomes a plasma. All right, let's continue.
But I'm at the house.
Oh, shut up. I don't know.
Is this in scientific? No, I'd leave it, just because it's such a small number. You could write 3 times 10 to the third, that's fine. Yep. Okay, this is the next one that's different. This is the difference here. So let's take a look.
The difference between the atmosphere and
Yes, now this is the difference here again. Notice what I circled on the board. It does not say mean radius. It does not say orbital radius. What does it say? Mean distance. So what this problem is giving you, here's the Earth, here's the Moon, it's giving you the distance. So for this problem, you do need to take the Earth's radius and the distance you have to get the orbital radius. Again, the goal is always to find the distance between the center to center. Okay? So again, I really should include the Moon's radius, but it's so insignificant, so I'm not. But the real distance we're given here is 3.84 times 10 to the 8. That's that distance right there. But we want to figure out the length of r, which is from center to center. So we have to tack on the Earth's radius, because that adds to the distance. That's this part here. The Earth's radius plus h. H is really just this distance here, plus the radius of the Moon. But again, the radius of the Moon is so small compared to the Earth and its distance that we just completely ignore it. Okay, any satellite that's orbiting something, we don't really include its radius. Even though, if you ever go out to work in astrophysics, you work for NASA or some sort of space organization, you would definitely include the radius of the Moon. Because you need to be precise to the nearest, 30 digits. Okay, we're not talking like estimations anymore. You have to be very precise. Little, not imprecisions, what's the word? Little errors or imperfections, thank you. Little imperfections along the way will accumulate. If you're in calculus, you know the word propagate?
Yeah.
A propagated error, that's exactly what it is. A propagated error, as we said in here even last time, is if you round something, and then you round it again, and then you round it again, then maybe you multiply by a number that's also rounded. These errors that you keep rounding are going to accumulate.
Didn't that happen?
Okay.
It was just a thing.
That was units. The Challenger explosion? That had to do a lot with units, and they had the rings that hold together the fuel, the rockets on the side that actually hold the fuel. The rings were not holding together. The force on them was too much that they split, and that's what caused it to explode. But it was because some people screwed up calculations along the way.
It was like we had a rocket launched fuel, and they were almost behind the Moon.
Oh, Apollo 13. They had to whip around the Moon? Yeah. Yep.
And what happened?
Well, they couldn't land on the Moon. They had to use the Moon's gravity to slingshot around the Moon because they lost a lot of their oxygen when they were doing something. One of the oxygen tanks broke or something like that. So they couldn't actually land on the Moon. It's a whole story about how they couldn't land on the Moon because of what. So again here, when you plug in this R down here, make sure you use this value, please. Again, it doesn't look like much of a big difference. It really isn't. If you look at the two numbers here, see that? The radius of the Earth is much smaller than the distance between the Earth and the Moon. This distance is huge. This distance that we get added on is not much different at all. Okay? So remember, the radius of the Earth is not that significant, but we still use it. And that's the speed that we're going to get. And again, what is that the speed of? That's the speed of the Moon orbiting the Earth. Again, the Moon orbiting the Earth. Any questions so far?
More than.
I was thinking the same thing just now, okay? I was thinking the exact same thing, so let's figure that out. Shouldn't this be more than the answer we just got a minute ago?
Yeah, double maybe.
That satellite must be at a higher altitude than the Moon. Which is weird, I know. But mathematically, you're absolutely right. To keep up the speed. Oh no, here's why. Sorry. It's not geosynchronous. The Moon is not geosynchronous. That's why, remember we get the high tide, low tide? Because the Earth is rotating this way and the Moon is moving, so it passes twice. when it's geosynchronous, it has to keep up with the speed. And that's where it comes in with the like rocket boosters on the side. I thought the same thing, because technically the further out, the velocity should be higher, right? And I'm wondering the same thing. Why is that not higher? That's the reason why. Good question. All right. So what I would really like to do today is this. How much time do we have?
5 minutes.
5 minutes. Really? No. We have about 35 minutes.
All right, way to go. I believe that. There you go. For the lottery.
Today is Tuesday. Tomorrow, listen carefully. Tomorrow you guys work. We have one more thing to do in this chapter in circular motion. That's it.
When are we going on our trip?
We'll talk about it. We started with circular motion. Okay. We went to gravitational force. After gravitational force, we moved on to Kepler's 3 laws. So we've done 3 major topics so far. The 4th topic is torque. Guys, please listen. The 4th topic is torque, okay, which is very applicable to all the stuff that we do. So what I want to do today is just do like an introduction of torque, okay, and discuss what it is and how it works and how we use it in life, and then we'll get into the math and mechanics of it on Thursday. Okay? We'll try to we can look for a video on torque and look at it, maybe it'll give us help. What that does though, just for a time frame, to give you an idea of where we're at. So Thursday we look more at torque and look at its applications. The math behind it is very, very simple for torque. Okay, it's not a very difficult one. Which will put like Friday to be a review day, because we're done with the chapter. Which would make, well, Monday there's no school. Monday is teacher at a work day. You get to come to work.
Is anybody?
You gotta work, so do I. I still go to work. Don't give me, please. I'm coming to work and then I'm coming here for Now, stop. Monday is teacher to work day. So when you guys are at work on Monday, relax. When you're at work on Monday, we're not going to have a test, obviously. Okay? So if we review on Friday, that puts the test at Tuesday right now. Okay, if anything changes, we'll talk on Thursday. But you want to write that down. Again, today torque, Thursday more torque. We'll go to the mechanics behind it. Okay? Friday review, Tuesday exam. Or test, whatever you want to call it. Quiz, test, exam, whatever. Or chapter assessment.
For the teachers that go to work with the students, will they like go the whole day?
Yeah.
I think so.
No, they're not.
Guys, I don't know. I haven't been instructed anything yet, so I'm not sure. I assume everybody goes. Maybe your job? And Steve was there, so he didn't want to leave.
See what they do.
All right, let's start talking about torque today.
Do
You know what I'm saying?
No.
Are you still aware that it makes sense?
How does school be stupid?
Now, let's end the discussion about work, please.
We're doing work right now?
So, for this example, what I want to take before we get started, raise your hand, please. Give me some reasons or some places you might hear this word or see this or where it comes from. Mark. Cars, very good. Okay, you use this a lot to do with torque. You're looking at, for example, your front axle of your car. If one wheel turned this way, while the other wheel turned this way, it would impose a torque on it, right? It'd be like giving somebody an Indian burner. Have you ever seen that before? When they take your arm and they just twist it both ways and they get that burner in your arm? Okay? It's the same idea. That's one application. Another. Where else is here torque? Speed, give me more than.
Like going at a high velocity.
Okay, a high velocity comes from a high amount of torque in a car. Sure, that's one way to do it. Good luck. No. I never had. But it has to do with the speed of the motorcycle?
Probably, I guess.
Oh, have you seen it?
Yeah.
So,
That's what it is. That's
okay.
I don't know. Friction? No? No?
Yes and no. I mean, like if you're looking at, for example, if you're looking at a gear mechanism, you know what a gear chain is?
Yeah.
Okay, or gear, you're looking at, you have a gear here, there's another gear here, and they rotate together. Have you ever seen the inside of a clock before?
Yeah.
Or inside of a watch? You see all those gears in there? It's a gear train. Now, in a gear train, the gears mesh with each other, so they do apply some torque and there is friction in there. So you could really, if you're pushing your limits there, say that again. This is a much simpler example. I thought some of you would come up with right away.
A bicycle.
Sure, bicycle, anything that's rotating has torque, so definitely, anything rotating. But there's one specific application of torque that you use every, I mean, has anyone ever done any work as far as building stuff goes? Or any contracting work? Or helping out in your house? Like, you know, have you ever used a wrench before?
Oh, wow.
A wrench?
Yes, you're building.
How does the wrench work? Aren't you turning the wrench like this, right? You're applying a torque. So imagine you've got
What about the adjustable wrenches?
you got a hexagonal bolt.
Karen's never used multiple kinds of wrenches. So what?
Why is that one so big?
I said Karen's never used my hands for labor work.
Okay, there's a bolt. Now, you want to take a nut, for example. There's a nut on the other end. You put it through. You're putting it in a piece of sheet metal. Okay, and on the other side of this, you're taking a hexagonal nut. Okay, come on, guys. Nuts and bolts. We know what these things are, right? So here, you take a nut that is hexagonal. Now, if you took the nut on the other side of the sheet metal and you had the bolt on one side, you want to tighten it. So you take a wrench that is in the exact shape of a hexagon, okay? You put it on the side of it. So for example, for this one, your wrench would look like this. And I know this is a very large wrench. It wouldn't actually be this large, but that's what the shape of the wrench would look like. Again, it would fit. It would fit the curve perfectly.
Depending what you're doing. I hate the adjustable ones though.
Okay, there's a wrench. It depends on what kind of a wrench you're looking at. You can also have nuts that are octagonal, so it could be a different one. That's called a hex nut, really, because hex is 6. Okay. Now, when you apply a force, who's done this before with a wrench? There's some of us. Okay. Can somebody tell me what would you do and what wouldn't you do? Where might you put your hand? That's my question, really, Christian. Why at the handle? What are you doing? Okay, but I want to hold it right here and push. What's the difference?
One is it's harder to do it that way.
Why is it harder?
Because you had enough force.
You can't turn it. Because of the torque. Your hand can't turn like that.
It's like the way you're turning it.
Okay.
Which way?
You're on the right track. So it's hard to answer this question without the mathematics behind it. Because you have to say to yourself, well, why does it work? I want to show you the formula. You're going to see that the formula is directly related to R. R being the length of the distance from your applied force and the actual central axis. So, the simple example that I used last year that I'll use again is a door. I mean, come on. Have we ever tried to do this? You put your hand right on the axis and you try to close the door? Doesn't that take a lot of force? As opposed to just, I mean,
I think it's just you.
look at that. It's very different, right? If I put a force here at the end, it's very simple. If I apply a force on the hinge, it really is harder. I'm putting a hard force on that. Because here's the rotating axis right here. Again, this torque is swinging about this axis. It's a z-axis, okay? You think of this as like x and y? So, it's rotating about this axis right here. When it rotates about this axis, we want to figure out how far are we applying a force with regards to the axis. So here, this is called your lever arm. And we'll write this down in a minute. Your lever arm here is like 2 inches, right? What's my lever arm over here, though? 2, 3 feet almost, right? As the lever arm increases, the amount of torque increases. So torque is directly related to the lever arm. We call that R. Okay, R is the length of the lever arm. That's where R keeps coming up again and again. So for this example, what I want you to think about is this. The torque involved, which is that symbol that's not a T. Anybody know what that symbol is? Latin and Greek?
What? Tie.
Turn.
T-A-U.
Tau.
Tau. Very good. Tau. Okay.
You said tie.
Tau. Not tie. Tau. Tie is T-H-A-I. Tau. Tau, which is the torque.
Yes.
Or a Thai person, because they're from Thailand. That's where Thai comes from.
Yeah, I know, but just the way you said it though.
The way I did it, yeah.
So this is a torque.
Whatever. You didn't even spell it Thai anyway.
Torque equals force times the distance. Okay? Again, it's just like work. It's just like work. Remember, work was force times d, F times d, cosine theta? For this one, though, the hard part is this, and I'll explain where this comes from, but there's a sine theta here. Okay? Remember, remember back, work equals force times distance times cosine theta. Today, it's going to be force, again, times this now distance is really, and I want to write this down, we're going to call this the distance between the force and the rotating axis. And that'll make sense. And rotating axis. Okay? It's also called, like I said before, the lever arm. So in parentheses,
Why would they use arm?
lever arm. Think about a lever. If you had a crowbar, right? If you had a crowbar and you wanted to lift something, you would push down at the end of the crowbar, right? That's why they come up with a lever arm. That's where that came from. But you still are applying a torque. If you wanted to pry open a door, you would take a crowbar, put it in, and pull on the end of it because you're getting more torque out of it because your lever arm is bigger. And take a look. If R doubles, the torque doubles. Because these are, God bless you, these are directly related. If the force doubles, the torque doubles. This is all linear, no square. It's a very simple concept because of that. Nothing is square. We don't have to worry about it. No denominator, nothing. So if you double the force, you double the torque. If you double the distance from the central axis, you double the torque. So when you use a torque wrench, and this is a specific wrench, has anyone seen a torque wrench before?
Yeah.
What does it look like?
I don't know.
How long is a torque wrench?
Real long.
Yeah, keep going. Even bigger. So a normal wrench, say a wrench, a hand wrench would be like this long. Okay, if you're gonna use a wrench. A torque wrench is literally like this long, and it's this thick metal, and it's like usually red. That's usually the paint they color torque wrenches. It's real thick, and you want to use it. You know what? Firefighters, for example, if they have to open up the thing, they use a torque wrench. Okay, that's what they have to use there. So they get this big wrench and they push down on it because they have that lever arm that's much longer. That's why they're able to open that. Try using a little wrench on that thing. Good luck. You're not going to get anywhere. There's so much force you need. So you make a longer lever arm, you push down with less force. Okay, you get the same torque. It's like a pulley. It's a mechanical advantage. That's exactly what we're going to lead into. That's exactly right. It's a mechanical advantage.
Say I have a bike and one of the balls in the back.
Oh, we started. Same handle, same size as the handle. Like they were longer, or you apply more force. So you put the wrench on.
I did.
Well, that's much stronger than the arm.
You ever done that? I can't do the car.
What?
Because I can't do
Position at 10?
No, my left. It's messed up and I can't. If I was doing my right.
No, what I'm saying, you either need to apply force, or you need to apply a longer wrench. And a torque wrench is usually adjustable. The end of it, you can adjust it so that it'll fit on any angle. That's the reason for it. So you can use it.
What are the ones that do the boys on me?
That's a ratchet. Those are awesome. Ratchets are great because you can go click and then click back, and the reverse direction does not apply force. That's really cool.
You know that they're making screwdrivers now?
Of course. Oh, they've been out for 10 years, man. You gotta get those. You get the head of it that was specifically made, and when you turn, they click back, and you can change the head of it, pop the films out, and put a little bolt chamber in it, and you can use that. I put the other day I was putting together a tool chest in my place. I had to put together a whole tool chest for all the tools, and what I was doing was I was sitting there and using exactly that. I was using a screwdriver with the end that has a bolt on it and adjusting and going back, adjusting, because when you go in the reverse, it doesn't actually loosen. Those are the new ones. They're really good.
What don't you do?
That's like the $300 worth of tools more in the back.
Is that like the same color?
You can't read Spanish. You get meters.
The most basic lever is the C-sharp. You have a central fulcrum and you have a force on each side.
You know the thing when you go like that and just start going.
A ratchet, yeah. He's talking about a ratchet. You just go, it goes click, 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 click. Yeah, it's silver. It's got the end on it.
Yeah,
You could also use a hand ratchet that now screws like a screwdriver.
Okay.
Those are all torque, but it's easier torque. That makes it easier. Okay?
Way easier.
It really is. Like click, 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 click. Instead of doing this and then this, and then especially when you're in a tight spot and you only have a little entry, you want to get that little click. You can't go around. It's so useful. So, theta is the tricky part. Not a line. What we're looking for, I'll explain this out. Christian. Because what? Word is cos theta. I'm going to explain why it's sine theta now. Okay, hold on. So let's take a look at an example. We're going to go over why it's sine theta now. If we have, let's say we have a beam. Okay, there's a
Oh, the
beam.
gymnastics thing?
Any beam whatsoever. I'm going to make it fixed with a rotating axis right here. Okay, very simple example. A very simple example could be a pendulum, but that was a beam. Imagine a pendulum swinging back and forth. But the pendulum itself, there's no rope and a bob, there's no rope and a ball at the end, but it's just a beam, and it rotates, it just swings freely. Okay? I'm trying to think of a better example of this, but
I can do it.
a beam, what's a beam, guys? Like a piece of wood or a piece of metal. So imagine you have some sort of piece with a bolt through it, and you're going to apply a force at the end so that this thing will turn, so that it's going to rotate. Okay? Again, we're doing this so that it will, rotate like this. We're going to do very basic right now. On Thursday, we'll get into the real math behind it. These are basic stuff. Now, let's go through this. Here's what I want to talk about right now. We're not talking about R or pulling and pushing. I want to talk about the angle. Okay, the angle is what's important. Now, let's think logically for a second. If you had a torque wrench yourself, and you apply the torque wrench to this bolt, so say you're uncapping a fire hydrant. Okay, fire hydrant's going to get uncapped. They apply the torque wrench so it's at this angle. So it's like this. Wouldn't you just push straight down? And then wouldn't you start pushing this way? And then wouldn't you start pushing this way? And then you start pushing this way? Aren't those all tangents to the circle, really? Again, if the torque is here, so here's the torque wrench, it's caught on here, and I wanted to loosen it, or in this case it would be tightening it actually. Say I was loosening it, just to keep up with the thing. Okay? So this would be loosening it, taking the bolt off. Okay? Counterclockwise is loosening. So, if I wanted to loosen this, I push down. Now, once it gets to here, okay, now the lever is there, or the torque wrench is there. Now I'm going to push there, aren't I? To get it to move this way? So my push is always tangent to the circle. Now, what kind of an angle does this make right here?
90.
A 90-degree angle when it's tangent. If the radius and the tangent intersect, geometric law, 10th grade. Think back. When a radius and a tangent intersect, they intersect at a right angle. That was one of our properties of circles. That's this right here. So we've got a circle where the tangent intersects with the radius, really. This is the radius. Now, the 90-degree angle is your best bet. So what we're trying to figure out, really now, is what if this angle is not at 90 degrees? What if for some reason you were not able to apply a force at 90 degrees, but let's say your force was at 70 degrees. Okay? Again, let's say your force was at 70 degrees. Think back to vectors. If I want to break this vector up, here's the Vx, here's the vector in the x direction, here's the vector in the y direction. We did this already at the beginning of the year. So, the one that really matters is which one, guys? The one you push down on, right? Isn't that in the y direction? Again, this is really so let's say this is your force of push, okay? This is your FPY. Let me write that correctly. Stay with me, guys. This is tough, I know. FPY. This is FPX. Again, when you are pushing at an angle, it's broken into two components. Part of it is pushing down, and part of it is pushing out. The FPX is not going to do anything except pull on the bolt. It's going to provide what's called a shear force in the bolt. It's going to make the bolt want to snap, actually. By you pulling out on this, think about it. If you push at an angle like this right here, you're really like pushing this way. So what you're doing is you're pulling this torque wrench this way now. So this FPX is pulling in the left. So that's just going to apply some force on the bolt. That's not going to help you move it. What helps you move it is the one that's acting down, because we want to know what's tangent to the circle. So FPY is what we care about. To get the y component, you use sine. To get the x component, you use cosine. So today, when we look at our formula, the reason we have F times R times the sine of theta is because we are looking at the y component of the force that we're applying. Okay? Not the opposite. Sine is always y. Inclined planes is when you switch. That's the only one. Okay? Inclined planes. But here again, we're trying to use FPY. Remember that. That's why this formula uses sine of theta. Now, the important part is to know what is theta, though. Theta is the angle between the force and the lever arm. So let's write that down, please. So if you want to write down the formula from the last page, theta is the angle between the force and the lever arm. Okay, angle between the force and the lever arm. So really what we're looking at is Fy. Again, you can write this formula as this. Tau equals Fy times R, and you're done. Because Fy is the force in the y, which is really force times sine of theta. So what I'm doing is I'm replacing F and sine of theta with simply Fy. So if you want to write the formula this way, you can, but it's going to be given to you this way. The reason you don't have to look at the x component is because right now we haven't started studying that. but it does have an effect. So when I studied solid mechanics in college, we looked at what's called a shear force. So imagine if you had a bolt, okay, and this bolt was holding together two plates of metal, and both of those metal plates were being pulled apart. Wouldn't that be putting a lot of force on the bolt? Wouldn't it make the bolt want to just shear in half? So imagine again, you have a bolt. Okay, there's a bolt. There's a sheet of metal connected to the bolt here. There's a sheet of metal connected to the bolt here. What if these sheets of metal happen to be being pulled apart, and the bolt is what's keeping them together? Isn't that going to put a force on the bolt this way, and a force on the bolt this way, which might cause it to snap or shear? That's why it's a shear force. Shear means to just split. So the Fx component, Kenny, that we were just showing here, this Fx, is applying a shear force on the bolt here. Okay? The shear force we're not really concerned with right now. If you continue to study engineering, you know what you're going to look at? You're going to look at the bolt, the properties of the bolt, the material it's made of, and find the limitation before it will shear. And you can find the shear force and say, is it going to exceed or it will be under? If it exceeds, it means it's going to break. So you can find the force that the bolt can withstand. You find the force that it feels. If the force that it feels is more than it can withstand, it's going to snap. Okay? So you are going to use it, but right now when it comes to torque, that's not torque. Okay? Good question, Kenny. It's a good lead-in. Again, guys, this stuff, I know we're not going over all of it in physics. I talk about it. But seriously, study engineering, you do all this kind of stuff. This is the stuff you learn. And don't let the math bog you down too much, really. I know it's a lot of math, but you can always study like engineering science. You don't have to be an engineering major. With engineering science, you look at a lot of theory, not as much math. Okay, the math is tough, though. I'm not going to say it's not. Christian. You know? Sorry. Is it like friction? Not really. I mean, there is friction there between the plate and the bolt, but the force pulling it is what's going to snap. It's not really friction. It's equal opposite reaction. That's all. Anything has equal. Right? Normal force pushing back doesn't have to be friction. It could be friction. There's no motion though. So there's no, excuse me, there's no kinetic friction. There's only static friction between them. There's no motion, right? It's staying still. All right, so just to end, here's what I want to do. We'll do a very simple problem today. Tomorrow, or rather Thursday, we'll get into more complicated stuff. Take a look at this problem. Okay, when you see engineering specs, this is what the kind of stuff they usually draw. They draw the center line through whatever you have circles. This is where the force is being applied. So we're going to need to figure this out. We're going to say that the length of this beam.
Is the arrow pointing to the line or just the object?
The arrow is the force that we're going to apply on it. Sorry, the arrow is the force. I was about to label it. The length of the beam is 3 meters. Okay. We are told that the bolt needs to be set in at a distance of 0.1 meters. Okay, so 10 centimeters into the beam, you're going to have a bolt. The force is going to be applied symmetric to the bolt. Okay, so again, the same thing on both sides. The question becomes, if the force is equal to 50 newtons and the angle happens to be 30 degrees, find the torque. Find the torque on this object.
So it would
Okay?
be...
Find the torque on this object. Figure it out. Figure it out. Okay, again, the force applied is 50 newtons. The angle it's being applied at is 30 degrees. You're told that the whole beam is 3 meters long. There's a 0.1 meter gap on each side for the bolt spacing and for the applied force, which you have to have. You're not going to really apply it to the end of it usually. It might snap. And then we want to figure out what the torque is. Figure it out on your own. You don't need to answer the question out loud. That's what you got to figure out.
Wait, there's 0.1 meters.
Again, guys, you're finding the torque. You need to know the force. You need to know the angle. You need to know the lever arm.
What am I looking for?
I'm not going to tell you. I want you to think about it. Guys, I'm not going to tell you the answers. Think about it for a second.
1 amp.
Oh.
Look at your definitions in the equation we wrote down a minute ago. What is your actual definition of R? Read it to yourself. Read it to yourself. And then look at the problem again, and it might make it easier. Read the definition of R to yourself. Got it? If you got it, just write it down, guys. That's fine.
Yo, read. It tells you.
He tells you if you're reading. He's right. He's
I
right
am
there.
reading. All right,
Not reading.
If you got it, just write it, please. Just write it for now. Don't worry. Well, you could calculate it because you know what the sine of 30 is going to be.
But also, I feel like
Yeah, right. Sine of 30.
Yeah.
Sine of 30 is a reference angle. You know what it is, Richard? You don't need a calculator? You don't need a calculator?
He actually solved it.
Can we get negative?
Like the setup? So they got R wrong? I thought I had it wrong. It's wrong, don't look at it.
This
But it says the distance between. So what is
Between
it?
what?
Point one
Force and what else?
rotating axis.
Where is it rotating about? The bolt. Where's the force being applied? A little bit in. So what is the distance between
The
them?
both is a little red dot.
So you would have to.
Kenny got it right away, but I didn't want him to tell everybody.
What's the unit?
Mr. Howe. Whose turn is up and sign is
Push it all the other side.
I forget which is which for your thing. I don't do the hand. Sine of 30 is one half. So that's what we'll get.
Okay, so the sign is
Christian's like, oh my God.
Guys, leave the units blank for 1 minute. I'll get to them in a second. There's a reason I'm doing that. Remember, R is defined as the distance between the force and the rotating axis. The rotating axis occurs right here. The force is really being applied right here. Now, you're not going to want to know what that distance is, and it doesn't matter. So what we're trying to figure out again is the distance between the two. Okay? So what is the actual value? 2.8. Again, 3 minus 0.1 minus 0.1. Okay?
So the force, so that line and dash line is the force at that point?
This is where the force is occurring. I'm showing you right on the surface. So you draw a line down and see where that perpendicular meets. Okay? Again, what you're doing, guys, this is radius again, isn't it? This is like the central object rotating, circular motion. That's why it's in this chapter.
So we just look at the. I know, he does not gonna take. Wait.
Yeah, exactly. Exactly.
What's the units for?
That's what we're going to talk about in a second.
Yeah. I thought it was 2.9. Times 1/2.
30.
You want your pencil back or no? It's never read it.
Sine of 30, everybody? 1/2.
That's a little tight.
Half of 50.
140. Sure.
25. I didn't mean that. I'm trying to do 2.8. It's going to be 1.4 times that.
70.
Yes, exactly 70. Very good. Now, the question becomes this. And please, you got to write this part down because this is very confusing. When we did work, remember work equals force times distance?
Yes.
And we got joules for work? This is not joule. This is called Newton meters. Okay? Because this is a Newton. This is times a meter. And when we did work, we said that force times distance was Newton times meter, which became a joule, we said, right? For torque, you don't use joules, you use Newton meters, and you write it the way I was showing you the other day. Not minus, it's just Newton meters. Okay? This is not a minus sign, it's a long hyphen. It's a long hyphen.
That's the end.
That is the answer.
It's two minus signs.
Okay? Multiply these three. Make sure you're in degrees.
That's like, I'm not in
You know sine of 30 though, Karen, so don't use count. The bolt, because that's what it's going to rotate about.
Like what we don't like.
Remember, the bolt is there holding it in place. We're going to apply a force star, and it's going to start to rotate. It's going to rotate. Guys, in case you're wondering, because the rotating axis sometimes can be confusing, think about the motion of the object if you pushed. Wouldn't it eventually start going like this? And then go off the board and then come back down around? So where's the rotating axis? It's right here in the center. That's what it's rotating. Just like this door. You need to look from a bird's eye view. The rotating axis is literally this hinge, and this hinge. You can hear it. It's rotating on the hinge. So the axis is straight up and down. So in three-dimensional view, you have to look down. Okay, this is like if I had it just here, and I was pushing up, and it started rotating like that, or down.
Can you look at the
The force to the rotating axis, that distance. And again, remember guys, you're looking right now at the perpendicular distance. That's the difference here.
That's right.
You might want to listen to this because a lot of you are going to confuse this up. You are looking at the distance from here to here. If you actually found the distance between the applied force and the bolt, it's really this hypotenuse. You see that? But we're looking, again, for torque at the perpendicular distance. Okay? The perpendicular distance. So if we want to go back and add that in, so if anybody gets confused, the perpendicular distance between the force and rotating axis. If you want to add the perpendicular symbol in to your definition here, I recommend it. Okay.
I was wondering if the other project we were just looking at, it was like,
I forgot.
you were saying that like, point 10 on each side was, like,
The gap.
the gap, but, why on the opposite side of like of the vault, it was not included into the radius? Yeah, but I mean like,
No, he's right. He's exactly right. The force was applied. The force was applied. Where's the problem? The next one. Sorry. The force was applied a tenth of a meter from the end. The rotating axis is a tenth of a meter from the end. So what is the distance between the rotating axis and the point of application? It's not rotating around here.
because they told you, right?
Sure, but you're always going to be given that. You have to know what it's rotating about. There's always going to be some sort of a pin. We call it a pin. And when you study engineering, you're going to call it pin fix. Pin fix. Because pin represents anything. A bolt, could be a screw. We call it a pin. So this is the pin location. The distance between the pin and the actual force is what you're looking for. Because that's where it rotates, at the pin. Okay? For tonight, here's what you want to practice.
I'm not gonna find the grade.
You guys have 2 days, I know that, okay? Tonight and tomorrow to do this. 2 nights of homework you're getting. Read one part tonight and then do the problems tomorrow. Not including other homework, no, sorry.
Yeah.
This thing was so hard.
Well, the problems they did that have A,
Special
B,
sucks.
yeah.
Second day.
Okay, split it up, please. Do one night, do the other night. You're reading 3. I recommend you read first, though, as always, okay? If I give you a reading, read first. The reading, you're going to get to this part where it talks about the sine of torque, and the sine of torque has to do with which way you're moving. So let's quickly just discuss that so you're not confused. If you're moving clockwise, okay, we're going to call that positive torque. We're just going to consider that all year, like we talked about the other day. We said the same thing. Anti-clockwise is negative torque. Anti or counter. Both words are acceptable. Anti was used forever, then they changed to counter. I don't know why. Anti-clockwise and clockwise, okay? So it does. If you're pushing up, so the example we just did would have been negative torque, right? Which way did we push the last example? Wasn't it pushing down over here? So it would have rotated like this. The last example would have done this. So that was negative torque. So if I want to go back, I really should apply a negative sign on the end of that. Again, people listen carefully. The last example would have rotated this way. A rotation anti-clockwise is negative, so simply apply negative. Okay? What are you laughing about?